Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it. Juno's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. And we do this over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere. A magnetometer is, it's best to think of it as a fancy compass. Unlike a compass that just records the direction of the magnetic field, our instrument tells you both what direction the field is in and what the magnitude is. And we can measure that very, very accurately to 100 parts per million. Juno's magnetometer is another in a long line of magnetometers built here at Goddard Space Flight Center, following designs developed by Mario Cunha years ago. Our instrument is between 1 and 2 orders of magnitude more accurate than anything that's flown to Jupiter before. And of course, part of that is the result of the star cameras that we're able to fly with our sensors so that we can determine the absolute orientation in space of these sensors. If we did not know the orientation of the sensor as well as we can determine it with the star cameras, we would lose accuracy in the vector measurement. So we carry 4 star cameras with our 2 magnetometer sensors. These have to be held in the same orientation with respect to each other under very extreme environmental conditions. So we designed what we call a magnetometer optical bench. It's a special structure, about a square foot in size, that is made of a carbon silicon carbide material, almost impossible to machine. But once it's fabricated and the sensors are assembled, they act as one. And that's one of the reasons why we can achieve much higher accuracy than has ever been attempted before. We hope to learn more about how a magnetic field is generated by dynamo action deep in a planet's interior. For me, the great excitement is the opportunity to look down and get the first clear, unobstructed view of what the magnetic field looks like on the surface of a dynamo where it's generated. It's always incredible to be the first person in the world to see anything. We stand to be the first to be able to look down upon the dynamo and see it clearly for the first time.